I'm Grace Hwang. I'm from the National Institutes of Health, and I've been very intrigued with organoid intelligence as well as following the neuromorphic community for the last several years. So let me move forward here. And of course, these are my mandatory disclosures. I have none. And what I want to do right now is pick off where our first speaker left, which is talk about health and AI and flexible engineered learning systems. To start, I think this is a set of wish lists that applies to any technology that would be adopted in health, whether it's a wearable, an implantable, or sensors. The technology needs to adapt with the users and their natural ecologically valid environment via in situ learning. What I'm really referring to is if you have a deep brain stimulator and you go to the doctor and you're optimizing that 90-minute a study, and then you go home and your physiology changes, you want that device to change with you. And oftentimes today we live in a set and forget paradigm. So the devices work, but are they working optimally? All right, I see a thumbs up from the panelists. Now, again, second bullet is interpretability and explainability. And this is a point that our first panelist made. And it's so important. We need to understand what our algorithms are telling us so that it could be useful for predictions. We need to understand, let's go into this third bullet, is reliability. We need to understand whether the algorithm itself is confident in the answer that it's providing. And the fourth bullet is whatever technology we adopt has to be ethical and fair and not have built-in biases so that there's public trust. And we must ensure user safety and privacy. I know there's FDA, and FDA is beginning to approve AI devices, but AI is new to all of us. So we're all learning. And one thing I often see left out are the user and patient and caregiver perspectives. And it is so important as you develop technologies to include those different perspectives right from the get-go, not as an afterthought. And even getting the insurance companies involved is helpful so that the technology you develop will be adoptable in the future. Because if it's a great technology, but nobody will insure it, it's not going to succeed. And then, of course, there's our favorite things as engineers: low size, weight, and power, data efficiency. Data is going to be a big challenge. Data is a huge challenge for AI. Data governance is likely going to be a challenge also for neuromorphic approaches, but at least we think neuromorphic should be more data efficient. And maybe the interface between edge and cloud, could lead to some wins. Whatever technology that's going to succeed, it should be unobtrusive. You don't want a technology that people won't use. Okay, that will not be helpful. And it has to be accessible to all people of social and different economical classes and to persons with disabilities. And of course, I would love for everything to be affordable. Although some people in the room are probably interested in making money. I'm on the other side of coming up with funding opportunities to seed research. So for this group, I was thinking, well, what components of neuromorphic systems directly impact healthcare and neuroscience? And to answer that question, I actually found a 2022 roadmap on neuromorphic computing and engineering. A few people in this room may have contributed to that roadmap. And so there are some obvious applications like biohybrid systems for brain repair, event vision sensors that we've already heard quite a bit about today, embedded devices for neuromorphic time series assessment, such as sleep tracking, EEG-based brain biomarkers, EMG processing using wearable neuromorphic technologies. There's, I think, another area for soft neuromorphic materials, and I really haven't heard a lot of that here today, but I think that's out there. And of course, there are neural stimulators to monitor and relieve symptoms, whether it's DBS, whether it's seizure prediction, Parkinson movement, alleviation, pain alleviation. And of course, we've already heard at this conference about neuromorphic audition. And I think robotics has a place in healthcare. But again, I didn't really hear much of that at this conference, except for the Carlson poster. Now, in addition, in the neuromorphic roadmap, there were different categories: algorithms, circuits, device, and materials. This is a little different from healthcare, but I think computational neuroscience is an area that would continue to bring new concepts to neuromorphic engineering that could then feed back into the healthcare ecosystem and bring value in ways that we haven't thought about yet. Under the circuits column, I highlight large-scale neuromorphic computing platforms, because, as we've already heard from the guy from BrainScale, that's an analog hardware that runs at least 1,000 to 10,000 times faster than real time and can confer many benefits from a mod sim perspective, stealing that from Brad. And of course, under the device materials category, we just heard about organoids. So my interest in organoids actually started initially as using cells and organoids to be a new computational substrate for biocomputing. And it's really interesting to hear it the other way around, where you're now using neuromorphic devices to train your organoids to then become intelligent. So I love this reciprocity, and I talked about that on day one. Anyhow, so I won't belabor the details. How much time? I want to give a shout out to the people that did contribute to this 2022 roadmap that I just went over very quickly. I think Tom's in the room, right? Or was? Okay, I won't call them people. And here's a snapshot on the biohybrid system that was featured in this roadmap. And the idea is that functional biohybrids would merge the concepts from regenerative medicine and neuromorphic engineering. And the symbiotic interaction between the biological and the artificial counterparts and the biohybrid graph is expected to achieve controlled brain regeneration process. This is, of course, it's not here yet, but it's looking out into the future. As far as using EMG and wearable neuromorphics, EMG, as you probably all know, measures motor neuron action potentials, and the current processing involves filtering, amplification, compression, and feature extraction in time, frequency, and that's typically done by deep learning. But the thought here is that neuromorphic offers low latency and low power, so perhaps that would be sufficient advantage to want to move towards using neuromorphic approaches. There was just a paper that was published by Giacomo Valle and Elisa Donaccia on neuromorphic prosthesis for sensory feedback. So I don't know if they're here at this conference, but I thought that was a very interesting approach, whereas realistic simulations of natural sensory processes uses computational expensive processes, and that's not suitable for embedded electronics. So the idea of using neuromorphic approaches might give artificial proprioception and help with prosthesis for persons with disabilities, for example, who would benefit from having feedback in real time, because you don't actually get feedback from hand prosthesis, or you can, but it's not common, and that's a challenge for persons wearing prosthesis. Now, another thing I found while coming out here was that Intel had a collaboration with Accenture back in August of 2020, where they used a learning algorithm in a robotic arm that could adapt to objects with different weights, and it was a learning algorithm, and I don't have the details, but I was hoping to learn more about it here. So if anybody is aware of this development, if from Intel is here, I'd love to talk to you. And I'm almost done. And, we've been talking a lot about the lack of definition in neuromorphic and sort of pros and cons as to whether or not it makes sense to try to define neuromorphic with a little bit more stringency. And I love this slide from Brad Amy's paper back in 2018 or so. And it really helps to remind us that there are actually 3 separate tracks. And the purple track is the wonderful neuroscience that took 50 years to inspire deep learning, which then turned into the AlexNet, which has now changed our world and is ChatGPT, and some might even think it's neuromorphic. So I was the person in the audience that said, no, let's not call that neuromorphic. And I want to remind us that we're kind of in this green lane, starting with the Carver and Mead lineage of the silicon neuron that started off as analog, but is now obviously morphing into analog and digital. And, how are we going to rebrand ourselves? I think there's no disagreement that neuromorphic is an alternative efficient, offers an alternative efficient architecture and algorithm, but do we really want to try to compete with the next TPU and try to fight with the people that have $1 billion to train the next GPT at N, right? Or do we want to look for the places where we bring value in a unique way that they can't do, such as in situ learning for health, as an example? And so now just changing gears, I want to go back to the what I refer to as convergence intelligence, which is this reciprocal relationship between organoid intelligence and neuromorphic engineering. You know, I think it is such a great place because organoids are meant to be personalizable. You can take, I believe skin cells can even be reprogrammed to be stem cells and then to be differentiated into whatever it is you need to recover function. And that would minimize things like foreign responses, which is a problem for stem cell therapy, right? And so it's meant to be personalizable, whereas neuromorphic approaches are meant to be super efficient. So it feels like a perfect marriage of two different types of technology. And I realize organoids is nascent, but as a funder, you know, I see these three different research tracks, or at least two different research tracks, neuromorphic and stem cell research / organoid research operating very independently. And I also see the neurotechnology biomedical research track operating independently. So it would be great for there to be some kind of a dedicated effort across funding agencies. And I know there are a handful of representatives here for us to talk about how to facilitate this conversation of convergence. And this will be my last slide because I think with organoids, we don't have to just think about the brain, even though the brain is awesome. I think there are lots of other types of cells, whether it's musculoskeletal or visceral cells that are also plastic and learn and can give us insights. And there are also many different animal systems that might be of interest, especially if you're not interested in health. I mean, obviously sticking with humans is a good idea for health, but for the people out there that's just interested in the next wicked cool algorithm for robotics, you might be able to learn something from an octopus, right? That would be amazing. So I didn't get a chance in my talk earlier this week to talk about some of the challenges with organoids, and Francesca hit on some. But I think there are really big problems with replicability in organoids and understanding the connectome, the dynamics over that connectome in vitro. In terms of integration of brain organoids with other types of organoids, you know, the idea of smashing a retina into a cortex, into a musculoskeletal, that seems like a really niche thing that only one lab I'm aware of, or one or two labs have done. Long-term memory is a challenge for organoids research. To my knowledge, it's not been proven. Vascularization is another issue. If your organoid is bigger than a couple of 100 microns, how do you keep it happy, right? And then if we don't have an infrastructure for on-demand assembloid factory for closed-loop design-driven integration, organoid engineering would not be an engineering discipline, and it would just be a niche market. And so that's something I think we need to keep in mind as we try to move these fields forward. And with that, thank you.